Hello, everyone. I am Ting, the author of this paper. I am really excited to share our latest research with you. The topic of my presentation is improving the ability of thermal radiation-based hardware Trojan detection. Anyway, my talk will cover four main parts. First, let us talk about what this paper is all about, detecting hardware Trojans, or HEs for short. As you might know, HTs are a type of malicious circuit that can be stealthily inserted into ICs during the design or fabrication stages. Fabrication time HEs in particular are becoming a real threat. And so related research in this area is continually evolving. These attacks are practical, highly stealthy, and pose a growing threat to ICs because attackers at the fabrication stage can easily exploit unused spaces in the IC layout to carry out HT attacks. To address these issues, researchers have developed reverse engineering and side channel analysis. Our team has also been working on this, especially focusing on side channel techniques because they are so fast and cost effective. But traditional methods like using power or electromagnetic radiation often face challenges. They often need a golden chip or specific testing vector to trigger the HTs. Moreover, their detection resolution is limited, and factors like acid size and process variation make detection complex. So yeah, we turned our attention to using thermal radiation for HT detection. Previous research has shown that using TR for HT detection has a lot of advantages. It offers high detection resolution, can resist process variations, and comes with more practical detection conditions. Let us briefly discuss the detection mechanism used in existing TR-based methods. The essence of TR-based detection lies in the difference in TR between logic regions and vacant regions when the IC operates quiescently. Logic regions heat up actively, causing a rapid increase in TR, while vacant regions increase slowly. So if an HT is inserted into vacant regions, the TR in that area changes. By carefully analyzing the TRM of the IC and comparing with the design data, HEs can be detected without needing a golden chip or testing vectors. Despite their potential, existing TR-based methods are designed for ideal HEs that fully occupy at least one pixel in the TRM. However, in reality, HTs often spread out across several pixels. For instance, as you can see in this figure, some HTs only take up part of a pixel. When that happens, maybe the existing methods do not work so well. So yeah, our study focuses on how to detect these subpixel HTs. Subpixel HTs pose a realistic challenge for TR-based detection due to their transparent nature. It is really hard to ensure precise alignment of HT boundaries of the pixels, leading to a significant reduction in occupancy within each HT pixel. As shown in this figure, the HT occupies only a quarter of each affected pixel. Since TR changes depend on how much of the pixel is occupied, some subpixel HTs may evade detection using existing methods. Here's an example. So the red and blue lines represent fully occupied and vacant pixels respectively. The TR distinction between them is pretty significant. But when an infected pixel is only partially occupied, it starts to look like a vacant pixel, making it hard to tell if there is an HT or not. So how do we detect these subpixel HTs? Do we need to get our hands on more advanced equipment? There may be other approaches. We noticed something interesting: mechanical vibration from thermal cameras, which is usually seen as noise. This noise is difficult to completely eliminate and will complicate TR distinction between suboccupied and vacant pixels, as you can see in the figure. But if we look at it differently, this vibration might actually help us out. It can cause the HEs to shift positions slightly. This heightened variability can increase their pixel occupation in certain directions, which makes the TR distinction more noticeable compared to when there is no vibration. So this observation got us thinking, what if we could use this vibration to our advantage? However, one problem remains. How do we find out which direction of vibration will best enhance this TR distinction for detecting subpixel HTs? So the HT bias towards the direction of vibration as shown in the figure it's really challenging to identify a single direction that optimizes detection for all HTs. So we need to change our thinking. So instead of trying to find the perfect direction for all potential HTAs, we can detect them by looking at all directions separately. If an HT reaches high pixel occupation in any direction, we are more likely to find it. So with this in mind, we propose a new HT detection framework called NICE. NICE works by categorizing terms into several sets based on vibration direction, then detecting HTs by traversing all directions. Finally, we combine all the results to get a more accurate detection of sub-pixel HTs. So direction-based TRM classification is a key component of the NICE mechanism. This whole process involves identifying the dithering direction within pixels at each sampling time. The challenge is accurately measuring this tiny invisible dithering. Fortunately, the correlation between pixel occupation and TR increment can help approximate possible dithering directions. So here's an example. By looking at the IC layout, we can see whether pixel occupation is increasing or decreasing in each vibration direction. Then by calculating the change in TR between sampling times, we can estimate the possible dithering direction. Finally, by analyzing the convergence of all pixels dithering, so we can identify the vibration direction across the entire TRM. So to ascertain the trend of pixel occupation, we actually developed a linear regression model to delineate the relationship between pixel occupation and TR increments. So we to calculate pixel occupation from the IC layout and extract TR change data from the TRM sequences. We use all the pixel data to fine-tune the model. Subsequently, the model utilizes the TR increment of each pixel to reassess its occupation at every sampling time. So based on a threshold set for occupation change, we categorize the occupation change into 3 classes corresponding to possible dithering directions. So the dithering directions for the entire TRM are determined by analyzing the convergence of all pixels at the same sampling time. It is well known that image dithering affects all pixels equally. So by analyzing the data statistically, we can pinpoint the most likely dithering direction. So here we use the soft voting method to determine the most probable dithering direction for each TRM, and then group TRMs in the same direction into our dataset. So in the HT detection stage, we analyze the TRM sets for each direction to distinguish between logic and vacant regions using the KES statistic and the Putte criterion. Previous research has shown that the TR changes in logic regions follow a normal distribution. So using the KES statistic, we can extract the statistical parameters for these logic regions. Then because of the TR difference, we can distinguish vacant pixels from logic pixels using the Putte criterion. So by comparing this with the IC layout, we can identify potential HT pixels. Usually any extra logic pixels detected in any direction are considered HTs, but if these extra logic pixels match logic regions in most other directions, the result needs to be corrected. To implement NICE, we developed corresponding software and hardware systems. So our hardware system consists of 3 major parts: thermal camera, support and isolation platform, and low noise module. So the support platform and XY parental platform allows for adjustments to accommodate different thermal cameras and ISO sizes. So the isolation platform and the low noise module effectively mitigate the environmental interference, making NICE suitable for deployment across various environments. Our experiment scheme consists of 3 major components: an equivalently approach to implement HTs, detecting HTs in statistical analysis. The equivalently approach is employed to implement HT, which is really challenging to implement in large numbers within the real IC. More specifically, we just randomly remove some logic regions from the IC layout. These regions appear vacant in golden references, but remain logic in the actual IC in our experiment. All logic pixels can be treated as HT, and each pixel is iteratively detected. Our experiments showed that NICE can actually detect subpixel HTs with a detection rate of up to 91.82% and a false alarm rate below 9%. That is a performance boost of over 47% compared to the previous method. We just further conduct experiments with various HD sizes to evaluate the detection capabilities of NICE, including HDs larger than a single pixel and those smaller than one. The results show that NICE can push the detection boundary of TR-based methods from more than 2 pixels to only 0.7 pixels. Considering the capabilities of thermal cameras the size of existing HDs, NICE enhances thermal camera capabilities covering recent HD designs. So, for instance, while previous methods needed a 12 micrometer thermal camera to detect HDs under a 130 nanometer process, NICE can cover those HDs with a 15 micrometer thermal camera. This means that NICE enables a more flexible and cost-effective selection of thermal cameras for TR-based methods without having to rely solely on more advanced equipment. We also conduct sensitivity analysis experiments for the number of TRM samples, the classification threshold, and the white noise. The results just showed that the robustness of NICE. So in conclusion, in this paper, we present NICE, a novel method exploiting the potential of noise for TR-based edge detection. It can detect sub-pixel HDs with high performance without needing a golden chip or special testing vectors. It can actually enable a more flexible and cost-effective selection of thermal cameras for HD detection. So that is all for this report. If you have any questions or suggestions, please contact us. Thank you for listening.